We're going to continue talking about economic growth, and we'll begin by discussing a specific model of growth called the solar model. And from that, we'll talk about catching up growth, the importance of the rate of investment, whether countries are expected to all converge ultimately to the same level of growth, and ideas about the contribution of new ideas, that is, technological invention, to growth, and the future of economic growth. Now let's begin with a question. And the question goes like this. If we're talking about real GDP per capita growth, why is it, for example, that an economy like China, or prior to that, the economy of South Korea, and way before that, the economy of Japan, could have been growing at a much faster per capita rate than has been the historic experience in the US. The US over the long run has been growing at about 2% real GDP per capita since the 1800s. As we know, in the last 40 years or so, several countries, including several in Asia, have grown at very fast rates and caught up to the US or come close to catching up to the US. So the question is why? Okay, well, let's look at an actual example. And the example we'll use is the period from 2000 to 2020 for China and for the US. And this data is something I've added to the slides using that website address you see there. It's quite easy. It's just you cut and paste, and you can easily select for all kinds of different permutations of growth in pretty much every country in the world. So if you ever need to play around with GDP stuff and you have to find some data, this website is really useful and easy to use. So here's an example of what needs to be explained. So you can see from actually prior to 2000 till 2020, growth rates for China and the US GDP per capita have been quite different. Now, to appreciate that they're different, you need to look at the scale on the right-hand side of each one. Look carefully. China's scale is different from the USA. And you can see that the USA, when there's a period of neither an extreme boom or a recession, the sort of average, is hovering around 2%. You look at China for the same period, and except for some dips, you could say the rate has been around 6%. And so here's our question. Why has China been able to grow quickly and the USA not so much? So here's the answer. It's quite simple. There's two kinds of growth. One is called catching up growth, and the other is called cutting edge growth. Cutting edge growth is where a country is growing and also inventing new things, inventing the automobile, inventing the airplane, inventing the light bulb, take your pick, inventing the internet to make it a little more contemporary. And if your country is on the frontier of doing all that stuff, it takes a while to grow, because to push the boundary of what's possible happens a lot more slowly. than progressing within what has already been previously discovered by somebody else. So to make the example specific here, of course China has the potential to grow much quicker than the US did, because most of the technology that China uses was already invented. Not necessarily by Americans. Some of it could have been invented in Germany or France or Russia or other places, India it could have been. So if you have all this technological knowledge and scientific knowledge already created, you can grow much more quickly than if you're in the position of having to invent the stuff for the first time. So that's why it's possible. But notice sort of the kind of logical consequence of this is, once the really fast growing country reaches the highly advanced level of technology, it is not going to continue to grow at 6%. It's now at the cutting edge growth stage. And so it's going to have to adjust to a slower rate. That's just the logic of invention and progress for everybody. We're now going to get into a model, and this model is quite a serious model. And it's serious in the sense we have multiple variables and we have formulas and things interact, and we get predictions and conclusions. Now, the good news is this model can be illustrated graphically with a picture. So although we'll do equations, your intuition can come from looking at the diagram, the image, the picture. And you should think of the equations as more like the explanation of the visual presentation, rather than try to work out the equations first, figure out what they all mean, and then go to the picture. That's the wrong way to do it. And it's useful for me now to point out a kind of fundamental human being fact. And the fundamental human being fact is that our visual ability, our visual intelligence, if you like, is phenomenally greater than our arithmetic, mathematical, symbol intelligence. And there's a simple explanation for that. For as long as there have been human beings, it's been very important to be able to interpret what we see. So, is there a bear behind that tree or not? Is that an antelope that I can maybe hunt and eat? I need to see. If you're driving on the road and you're merging with traffic, your brain looks at the other vehicle and your vehicle and the road, and you don't solve a calculus equation, but you in effect act as if you do, because you correctly, and the other driver too, you and the other driver correctly anticipate kind of the trajectory of what's going to happen if both cars continue on their path, and one of the cars will slow down or one of the cars will slow up, or both things, and you'll judge it correctly. So any problem, especially a math-related problem, convert it to a visual problem, and you're far more likely to get the intuition and the understanding much better. Unfortunately, this is kind of the opposite of how a lot of things are taught. Typically, you're presented with equations, with discussion of the equations, and then a diagram is slapped on at the end. That's exactly the wrong way around. It should focus on the picture, on the visual intuition. So let me put that to the side. That's a general statement about any kind of learning that has anything to do with anything that can be illustrated visually. and doesn't have to only be in terms of equations or words. So here's the solar model. The solar model has a production function. The production function has y on the vertical, and we use the letter y because that was the choice of labeling that was made way back in the early 20th century. So I won't get into the history. So some of these choices of letters have some history behind them. Just remember, total output of the economy is y. Total GDP is y. You can forget about inflation for this model. So that's the good news. Don't worry about inflation. Don't worry about correcting for inflation. There's no inflation. Everything is measured in constant dollar terms. So the economy has output y, and the inputs to produce outputs y are physical capital, which is measured by K, human capital, which will equate to education times labor. In other words, the amount of useful knowledge you have comes from taking education and multiplying by the number of laborers, the number of workers, to give us a total amount of sort of education out there. And we call that human capital. And finally, ideas, A. A is just a parameter that's either high or low or medium. And if A is a big number, that means your society has a high level of technology. If A is low, that means your society has a low level of technology. So got that? Total production, total GDP in the economy depends on physical capital. How many machines? That means how many machines you have, how many factories you have, how many tools you have. That's K. It depends on EL, and EL is E is like the education level of the average worker, and L is the number of workers you have. So multiply E times L to get a total amount of sort of educated labor inputs. And then finally, ideas, A, that's the level of technological production, idea sophistication you have. So a production function says that y is a function f of a, k, el. So look at that, y equals f of a, k, el. If a goes up, that means you've got productive invention. You've got new and better technology. So we sort of understand why everything else equal, total output would go up, right? K means if you have more factories, if you have more roads, if you have more bridges, if you have more machines, you can produce more stuff. So we understand why K is in there. And let me break down the E and the L. The L is just the number of workers. So the more workers you have, everything else equal, the more production you have. And E is sort of the average level of productive knowledge those workers have. So if you have really well-trained workers, the small e there is a big number. So you don't just have a lot of workers, you have a lot of educated workers. So that's the intuition of the production function. We are going to simplify the model by assuming that A, E, and L are constant. And by doing that, we drastically simplify the equation for output. Output is now a function of only one thing, the level of capital, the amount of physical machines and tools that you have to work with. So when we look at the diagram and we talk about the model, we're only going to have K as the causal variable, at least for now. So the idea is that if you have a society or an economy, and that economy has a certain amount of capital stock, then if we increase the capital stock, we expect to produce more output, more Y. So more K means more Y. So the analogy is to a factory, and the factory starts out with only a small number of machines. And at first the factory can produce a certain amount of stuff. And if you give the factory more machines, you will be able to increase your output. However, the intuition is, since the number of workers and the level of education and the level of technology is being held constant, increasing the number of machines will increase output, but eventually the benefit from having more K will lessen. The reason is you're getting more and more machines, but you don't have any more workers to use the machines. And you don't have any better technology either to help you. So it's sort of like a factory where you keep piling on by buying more and more machines, but you keep the number of workers and their level of training the same. You're going to increase production, but at a decreasing rate. And that's what we mean by saying because L is constant, an increase in K does imply an increase in the amount of capital per worker, K divided by L. But it's not going to be a continuous, rapidly increasing output. So here is our diagram, and we imagine that on the left we're starting out with 0 capital. You see capital, comma, K, that's the horizontal axis. And if capital is 0, so the factory has no machines at all, then output, which is measured on the vertical, output will be 0. Now, as we start giving the workers some machines to use, output will go up very rapidly because they were starting from 0 machines. So you give them their first couple of machines, yes, output will go up very rapidly. But if you keep giving them machines but you don't increase the number of workers, the increase in output from one new machine becomes less and less. And that's why you see the sort of increased output kind of flattens out as you keep on adding capital. You're kind of constrained by not having enough workers to use all the new machines efficiently. And we're going to use the equation y equals the square root of k as a sort of shortcut to get the correct shape for that diagram. It's a way to get that output increase to flatten out to represent what we call diminishing returns to extra capital. Extra machines increase output, but that you're getting a diminishing increase the more capital you have, the more capital you pile on. So the word we use is marginal product of capital. Marginal product of capital means if I have capital at a certain level, a certain quantity, and I add one more machine, I add one more unit of physical capital, how much extra output do I get? So on the margin means I add one more unit from where I was, how much extra output do I get to my total? So we understand that more capital should produce more output, but at a diminishing rate. MP subscript k diminishes because the first unit of capital is applied where it is most productive, the second where it is slightly less productive, and so on. So that's capital production and diminishing returns. And to repeat, the reason we're getting diminishing returns is because we are holding all the other factors of production constant. We're holding the number of workers constant. We're not letting the number of workers go up. We're holding technology constant. We're holding education of the workers constant. So that's why we can have a two-dimensional diagram. Only one factor of production, physical capital, is being allowed to change. And the vertical axis shows us output, total output. So we're going to talk about how total output is used. Total output is used partly to produce consumption goods, and that's something we understand. But total output is also used to produce the physical capital that the workers in the next period are going to be using. So output generates consumption, which makes people better off in terms of, they're consuming more. But output also is what generates the new machines that we will begin using in the factories. And that split of total output between producing consumption and producing capital goods is called a split between consumption and investment. Now let's be clear, the word investment here does not mean financial investment, nothing to do with banking or stocks or any of that stuff. Investment here means you're taking some of your output and you're going to use it in future production. And just to make the diagram simple, we will assume that this society has a rule that 0.3 of all new production will be dedicated to producing more machines. That's going to allow the economy to grow over time. You're not just consuming everything you produce, you're actually taking a share of that output, 0.3 of it, and dedicating it to investment. And investment means the creation of new machines. So, capital is output that is saved and invested rather than consumed. And when we say saved and invested, what we mean here is output that is used to produce new machines. There's no financial sector here, okay? There's no stocks or any of that. So for example, out of 10 units produced, let's suppose your total output this year is 10 units, then 7 will be consumption goods, and 3 of those units will be turned into new machines, new capital. And that's why we write the fraction of the output devoted to producing capital as 0.3. Now, so far so good. We are going to add another complication, though. The machines that we produce will depreciate. That is, they're not going to last forever. And we sort of need something like this to prevent the society from being able to effectively produce an infinite amount of stuff, because if capital never wears out, then in theory you could ultimately increase your production to infinity. You just keep producing more and more capital goods forever, and your output goes up, and you produce more capital goods, and there's no stopping point. So to be more realistic, and it helped to explain why society cannot just grow infinitely, we assume that those machines depreciate. They wear out. They need to be replaced. So for example, if you have 100 units of capital, and if you have a 2% depreciation rate, then if you do nothing, after 1 year, the 100 units of capital will become 98 units of capital. So we need to illustrate the force of depreciation on the diagram. So how do we do that? Well, to keep it simple, we'll assume that there is a constant fractional rate of depreciation of capital. So if you're at a certain level of capital, a certain percent of that capital is going to depreciate. It's going to go away. And since capital is shown on the horizontal axis in a linear way, then that means if you take a constant percent of K, you're going to get a straight line. So depreciation is a straight line function of the level of capital you have. The more capital you have, the more depreciation you're going to have. And that's why we use a straight line on the diagram to capture the force of depreciation. The significance of having a straight line depreciation rate like that is that it means the country cannot increase its capital stock forever. The country cannot increase its capital stock to infinity by just adding more and more capital. And the reason is that investment is this curvy line. The production of capital intersects the straight line depreciation line. So eventually the force of depreciation is going to be greater than the rate of investment. Sooner or later, no matter what you do, depreciation will be at a higher rate than you are replacing machines. So notice, even if we shift that green investment line upwards by having a greater investment ratio, instead of doing 0.3, let's do 0.4 investment, or 0.8 investment, or 0.9 investment, or even 100% investment. Everything we produce goes back into producing more machines. Because of the shape of the investment line, it curves, it flattens out. Eventually, that red line will catch up to it and intersect. Now look at the intersection point in this diagram at 225. That's a point at which the economy has a balance between the amount of new machines being produced and the amount of machines that are going away because of depreciation. So if you are at 225 on capital level, you're going to stay there forever because the number of new machines you produce exactly cancels out the number of machines that are depreciated out of existence. Another thing, if you are to the left of 225, if you are like at 100 on this diagram, 100 is a point where the rate of investment, the amount of investment I should say, exceeds the amount of depreciation. So if you are to the left of 225, you are building new machines faster than they are depreciating. So if you are at level 100, you're going to be adding on net, on balance, you're going to be increasing your capital stock. And what that means is you will be moving to the right along that capital line. You'll be going from 100 to 200, say. Now let's suppose you are on the right-hand side of 225. You're at like 300. If the economy is at 300 total capital stock, the force of depreciation, the amount of depreciation exceeds the amount of investment. The force of depreciation exceeds the rate at which you are creating replacement machines. So if you are at a point like 300, you're going to go backwards. Depreciation is greater than investment. You're losing machines faster than you're building them. So your economy will move to the left. Your position will move to the left. So what this means is this diagram says that if you're to the left of 225, you're building machines faster than they're disappearing, you will move to the right. You'll be on net adding more and more machines, and your number of machines will go up, and that's why you're moving to the right along the capital line. If you are at a point like 300, that's a point where the force of depreciation is greater than the number of new machines you're producing. So if you're at 300, you're going to be moving to the left on that horizontal capital line. You're losing machines quicker than you're building them. The only point where you're in equilibrium on your capital stock, the only point at which the number of new machines created exactly balances out the number you're losing, is if you are at a capital stock of 225. And that's why we call that the steady state level of capital. The steady state level of capital is 225, because that's the level at which replacement and new production are exactly in balance. Unless something changes, your economy is going to stay there forever. So here's a diagram that captures everything that happens. You've got the red line and the green line, and the red line and the green line are what really drive the model. They're really what drive the changes. It's the interaction between the red line and the green line that determine, are you going to be moving to the right on the capital axis? Are you going to be moving to the left on the capital axis? Or have you reached a steady state at 225? And the total production line, the blue line, is what tells you the conditions under which production occurs. It tells you how much production given a particular value of capital. So if you are at a point to the right of 225, you're going to go backwards. You're going to, because you're wearing out machines quicker than you're producing them. So if you're to the right of 225, you're going to move to 225 for capital, and that also implies a certain level of total output. If you're to the left of 225, you're going to be pushed to the right because you're producing machines quicker than they are wearing out. Now, if we stop there, we kind of know what the fate of this economy is. The fate, the only place that the economy can end up at a steady state is the level of total output consistent with being at 225. So it's natural to ask, is there anything that we can do to influence this situation? And there is actually one thing that the government, or society if you like, does have some control over. The only degree of freedom, as they say, the only variable that you can choose is the split between using your output for production of consumer goods or production of physical capital. So it's that investment proportion that is the one lever, it's the one optional choice that a government can make. So in our diagram, we do put it at 0.3 of total output. But if you choose a different level, you'll get that green line shifting up. So suppose the government decides through policies of various types to cause the rate of investment to be 0.4 instead of Y, instead of 0.3 of Y. That's like saying the government has introduced a policy whereby a bigger share of production is going to be dedicated to producing capital goods, machines. So what that means is now you'll have a new green line that is higher than the old green line, and it will intersect the depreciation red line at a point further to the right. And that resets the steady state level of output for all the sort of reason we talked about before. The society will move to a higher steady state level of K. So at this point, it's worth asking, do we then get some conclusion about economic growth in the world as a whole if we use this kind of model? And there's a prediction. If this model is substantially true, then what it predicts is that sooner or later, if all countries keep growing, eventually all countries will end up at some kind of steady state level of output and depreciation and investment. And once your country reaches that point, it stays there forever, waiting for other countries to catch up. So if you have a world in which rich countries have already reached some kind of steady state equilibrium, and they're not changing per capita production and consumption, and poorer countries are sort of to the left on the capital line, and they're at a position where production of new capital is exceeding depreciation, those smaller countries that are on the left of the diagram will keep moving to the right until they catch up to the steady state. So that's what we call conditional convergence. It's a tendency for poor countries to grow faster than richer countries. Another way to put the intuition without needing a diagram is that if I'm a poor country, I probably don't have much capital. So if I can save and build more capital, I'll be able to grow quickly. If I'm a rich country, I already have a lot of capital. I already have a lot of machines. So my potential for growing quickly is not very good. I've already got diminishing returns on my already high level of capital. So over the very, very long run, you'd expect countries to all catch up to about the same level of prosperity. That's conditional convergence. So a question suggests itself is, if countries approach some kind of steady state and they're supposed to stay there forever, how can you have a case like the United States growing for 200 years? And another sort of seemingly contradictory fact is, if you recall, the graph of world growth over history shows that in the last 200, 300 years, growth has been exponential. It is a sudden upward movement in the total level of production in the world. So that kind of seems contradictory to the idea that as a country develops, its ability to grow further decreases. So we're kind of puzzled. We'd like to know what it is that allows what seems to be growth beyond simple investment in machines. And what suggests itself is a couple of things. One is technology. All this time we've been assuming that technology is the same. We're just producing under the same production conditions and making decisions about how much to invest in producing new machines versus how much to invest in consuming what we've already produced. So there is a case that the Solow model leaves out something important, and the something important is technology. We've kept technology constant, but what if technology is increasing? Technology improves. Technology allows us to create new sorts of products that weren't even possible before. So that's what we'll talk about now. And what we like to use the word ideas, not just technology, because when we say technology, it sort of implies we're talking about a machine, and a machine needs to be produced, right? But the machine is simply a manifestation of an idea, of intellectual property, if you like. So that's where we're going to go now. We're going to say the Solow model gives us a partial explanation of growth, perhaps in the short run. I mean, it can explain why South Korea might grow quickly. South Korea invests a lot in creating new machines, and during that period, South Korea is willing to consume less as a proportion of output in order to invest more in creating new machines. And we sort of understand how that could cause a country to grow quickly for 30, 40 years. But what about long-run growth, like the United States over 200 years? There's got to be something more. Otherwise, the US would have reached a steady state long before now. So we're going to use the word ideas as a sort of proxy for technological advancement. And we're going to conceive of ideas that increase productivity. And given our initial production function y equals a times the square root of k, we need to think about changing the a. Up until now, we've kept a constant. A is ideas. A is technological knowledge. All through this, the only factor of production we've allowed to increase is k. So the next step is to allow a, the coefficient in front of the square root of k, to go up. So increase in a, everything else equal, now allows you to be more productive without having to sacrifice consumption to produce new machines. So when we think about ideas, which is sort of another word for technological advancement, technological advancing ideas. Ideas for increasing output are primarily research developed and implemented by profit-seeking firms. Firms that want to get an advantage over their competitors. And people who are creating new kinds of business. And people who want to maybe break into a field where the existing firms have a strong dominant position, and the only way to get an advantage is to have some kind of technological element that they don't have. Now notice, for a profit-seeking firm using new and better technology, there's a problem for society. If a firm invents some new great technology for producing automobiles, from society's perspective, we'd like that technological knowledge to be propagated through the whole of society. We'd like as many people to have access to that new technology as possible so that the whole society can benefit from it. But to the degree that productive new inventions are created by private profit-seeking firms, those firms are going to want to keep control and the exclusive right to exploit their invention through patents and copyrights. And it makes sense. Why would a firm invent $1 billion in creating a new drug if it immediately had to turn the formula over to anybody else who wanted the formula? They would have invested the $1 billion to create the new knowledge. They have to be able to make a profit from it. So even though in principle, in kind of their very essential nature, a good idea can be freely shared, but to the degree those inventions, those ideas are held by private companies for their own benefit, you're not getting what we call spillovers. You're not getting the propagation of the new technology to the rest of the country, to the rest of the industry, to all the people who could benefit from it. So that's the sense in which we have a problem. And it also means firms maybe don't have an incentive in creating new inventions that don't benefit them directly. If an invention might be great for increasing production, but it may somehow not be to the advantage of a particular firm. For their benefit, that technology may not be good or particularly helpful. So if we leave it 100% to the private sector, we are going to get new ideas and new technology, but not as much as society could benefit from. And that's why government has a role in improving the production of ideas. There are some ideas that are good, really useful, general ideas, but they're not sufficiently patentable. They're not the kind of good ideas that an individual firm can make a lot of money from. So there's a role for government. And the analogy here is that good ideas, new technology, is like what we call a public good. It's a good that benefits everybody, but cannot easily come under the standard property rights. So for example, clean air or a clean environment is obviously a good thing, but that's not a thing that can really be a simple market solution. Leave it to the private sector to create. Another point, considering what promotes the development of ideas, new ideas, is the size of the market, the incentive to create new ideas, new research, also depends, at least in the commercial sense, on the potential size of the market that can profit from it. So if I am a drug research firm in a small country and I'm only allowed to sell my new drug within my own country, and it costs $1 billion to invent this new wonderful drug, I've got a problem. My market isn't sufficiently large for me to recoup my expenses. So trade which opens markets is not just about trade in goods and I benefit and you benefit and we trade goods with each other, or even we trade services with each other. It's also true that the broader the world markets are and the more free they are, the more potential incentive there is for people to invent and try to exploit new and better technologies for production. The incentive for creating new and better sorts of products is greater if you have a greater potential market for it. So finally, we're getting closer to the US case, having an explanation for why the US has been able to be so successful. And it's to do with the environment for new ideas. So the generation of technological knowledge or good ideas, however you want to phrase it, depends, kind of like everything else, on the institutions and incentives you have in your society. So if we think about the kinds of institutions that promote invention, innovation, newer technology, it would include things like a society that allows and helps innovators to connect with what we'll call capitalists or owners of companies. Reliable property rights for intellectual property. So you invent something, no one can just come and steal it from you. And a high quality education system. So you sort of need a training and way to propagate out existing information, because people have to build on a solid knowledge of what's known before they can make new discoveries. So the United States on those things traditionally for 200 years has had a very good cultural and commercial and social and institutional infrastructure for supporting the creation of new ideas and their commercialization. So you sort of need both things. You can have a society with lots of great innovation, but if those innovations cannot be made commercial because, for example, there's weak or no protection of intellectual property, you don't have the incentive to do it. So it's sort of like a combination of things. So let's get more precisely focused on the protection of intellectual property. And the two methods are patents and copyrights. And let me talk about patents because they're the ones that apply mostly to new commercially relevant innovations and creations. So in the US case and in Western countries generally, patents are for the protection of intellectual property to do with new processes, products, and methods. And these are discoveries that could potentially be copied by competitors. And the always concern is that imitators have lower costs because they do not have to invent the original breakthrough. So if you allow imitators free rein, they will tend to drive innovators out of the market unless barriers prevent quick or illegal imitation. So this is why countries, by the way, which are moderately developed but don't have good intellectual property enforcement, can have a deficit of new inventions. They've got all the conditions except that there's no incentive to create something new that is costly and valuable, because it's going to be costly for you to create it, but then someone can steal the idea, or not steal the idea, appropriate the idea from you and use it for their own benefit. And in the US, patents typically give innovators temporary monopoly rights over their invention for about 20 years. So that's the sort of default. A patent is for 20 years. You create a great new drug. It's approved. You've got 20 years to recoup your money and make your profit. Here's Thomas Jefferson commenting over or about the benefit of spillovers. Spillovers are transfers of valuable knowledge, and to the degree we're not talking about patentable knowledge, it's sort of like a free benefit. He who receives an idea from me receives instruction himself without lessening mine, as he who lights his taper at mine receives light without darkening me. So intellectual property creation at some sort of fundamental level is not zero sum. Putting apart the sort of property rights side of it, new invention is productive in a way that creation of physical objects is not. If I use resources to create a machine for my factory, those resources are not available for you to create machines for your factory. It's sort of zero sum. But when it comes to intellectual property, new technology, and here we're talking about the pure knowledge of how to do it, the formula, as it were, that is not zero sum at its essence. It's not zero sum in its nature. And that's why the creation of intellectual property that's valuable in production is so powerful, because it is not using resources that sort of take them out of play for creating other things. There's a technical word we use, it comes from microeconomics. New productive knowledge in its pure sense, in the sense of being a formula written down, is non-rivalrous. Non-rivalrous means it's a good which is not zero sum. A rivalrous good would be like an apple. You eat the apple, no one else can eat the apple. But pure knowledge is non-rivalrous. Your creation of the knowledge does not diminish anyone else's ability to benefit from the knowledge. Even when we do have patents and copyrights, there is still a tendency for ideas to spill over and benefit other firms and consumers. And that's because ideas are fundamentally non-rivalrous, and they're fundamentally they're not material physical things that can wear out or have to be physically possessed. So we like to think that ideally good ideas should be shared. If somebody invents a new formula for a medicine, we want that to be shared. Yet again, though, we have the trade-off between the incentive to create the new invention, but then we want it to be used widely. So that's why we have patents, but patents have a limited time frame. The limited time frame means the originator can recover their cost and make a profit, and then after that point, the good idea can be shared broadly and generally. Spillovers are good. And that's why we have a system that needs to be well designed. So we understand government has a role, and the role can be better designed intellectual property system that encourages more invention for some kind of inventions that are valuable but maybe are not immediately commercially profit making. The government can invest in creating or supporting those sorts of invention and discovery. Of course, universities train scientists who do the research and develop new products. The kind of innovation that does not get private funding is very basic research into really fundamental things about the world. And those things generally are just not patentable. So if somebody discovers a new kind of element to add to the periodic table, you could not patent that. If somebody discovers a new galaxy, you can't patent certain sort of really, really basic knowledge. And yet that basic knowledge is the foundation for invention. So that's a role for government to provide grants and support monetarily. So at least before this year, which is 2020, up until 2020 began, the situation in world growth was fairly good. Growth in per capita terms was around 3% per year. And part of the credit for that goes to more invention, more new ideas. And the number of ideas you get generated is a function of population times incentives times ideas per hour. So there's potentially an upside in having the population of the world increase, because more people mean more good ideas, and because of spillovers, those ideas will propagate through the world. And if you have integrated markets, you are boosting the incentive to innovate. So there's a potential for economic growth to be even faster in the future than it has been in the past. But again, of course, this is what's possible. At this point, we're talking about what's within the realm of possibility, not necessarily predicting what's going to happen. So here we're into the takeaways, the two takeaways. The solar model tells us that countries devoting a larger share of output to investment will be wealthier, and the further you have to go to reach your steady state, the more growth you can expect to have. That's the catch-up effect. If you're a poor country, your potential to grow rapidly is high. Whether you do it or not depends on government policies and things like that. But it's also true that at the end of the day, accumulating capital, that is machines, and producing more and more factories, at the end, that is not sufficient to explain long-run economic growth. And that's where new ideas come in. Long-run economic growth, even by already rich countries, has to be explained through the generation of new ideas. So that sort of means if you want to be a leading country, like in the first rank, you cannot do it by having really good investment policies. You cannot have incentives for factory owners to expand their factories. If you want to be in the first rank of the most advanced countries, you have to be in the business of inventing new and better ideas, new and better methods for production, new kinds of products. That's where you have to be if you want to be in that very top tier of prosperity. And the final takeaway is that while good ideas are really valuable because of the spillover effect and the fact that they are kind of pure, what we call a pure public good, we have to have a system. We have to think about the problem of giving the correct incentives to create those new ideas. A great new productive new idea in its essence is not a material thing. It would be easy for a rival to take it and use it for their own purposes. So we have an important role for government in the protection of intellectual property rights with an appropriate trade-off, a sort of period that a company or an inventor can recover their costs and sort of make a profit. But after that period is over, the new invention, the new idea is now supposed to be free for anybody to use. And now we have a sort of balance between creating the incentive to create new ideas, but also we want to maximize the opportunity for people and firms to benefit from new ideas. So that's why we have a limited period patent and copyright, by the way, too. So there's this trade-off between providing incentives to produce new ideas and providing incentives or the freedom to share the new ideas. You need a balance, and you can't go too much one way or too much the other way.